Our goal was to analyze the flow around the cylinder at different Reynolds numbers, both visually and mathematically. To achieve this, our group decided to run the wind tunnel at 200, 500, and 600 RPM to achieve different Reynolds numbers. After collecting data, the entire experiment was repeated with tape attached to the front of the cylinder, which acted as a trip strip. Visually, the results were expected to look like this graph. The footage also appears to match the expected vortex pattern.
As shown in the test matrix, our group devised a plan for which speeds to test at and which tests would be tripped or not. When the lab was set up, the cylinder was already located here. Our group decided the cylinder was already in a good spot for testing and decided to leave it there because it was out of the way of the boundary layer and was in a good location for viewing. The cylinder was set up like this, with each port being separated from the other one by 15 degrees, allowing data to be collected from the entirety of the cylinder surface. The first 12 tests were run. Our group gathered data and visually assessed the flow visualization over the cylinder. For the next set of tests, our goal was to see how the pressure coefficient changed with the addition of the trip strip. Our group decided to put the trip strip on the leading edge of the cylinder, about 20 degrees offset from the top. We put this strip in this location because it would allow us to separate the boundary layer before it was ready to separate. Again, the group repeated the tests with the same RPM and sampling rate. This would allow us to compare the difference the trip strip had on the coefficient of pressure. After calculating coefficient of pressure at each port for each Reynolds number, we plotted our results in a coefficient of pressure versus theta graph. These plots accurately follow what we expect when comparing them to the envisaged solution plot. The envisaged solution assumes that the dynamic viscosity of the fluid is zero, which means the Reynolds number would be infinite. This means this solution is more accurate for turbulent flow with very high Reynolds numbers. This idea is clearly seen in our plots. As the Reynolds number increases from about 60,000 to 180,000, the plots become closer to the approximation. And for the tripped variation of each Reynolds number, the data follows the approximation even better, which is also intuitive since the trip strip induces turbulent flow. The only exception for this was the 200 RPM 60,000 Reynolds number graph, where the tripped variation is about the same as the untripped variation. This is likely because the fluid velocity was so low that the effect of the trip strip was negligible. Next, we plotted the magnitude of the coefficient of pressure versus theta in a polar graph to make the coefficient of pressure easily visualized around the cylinder. We flipped the axes and made the plot increase in theta in the clockwise direction so that the plots are coherent with our video, in a sense that the fluid is flowing in the same direction and the ports correspond with the correct theta value on the graph. We also used magnitudes of coefficient of pressure since negative values would be hard to interpret as they could be incorrectly associated as a positive value with the mirroring angle. The analytical advantage to looking at this plot is that there is a clear trend in coefficient of pressure magnitude in the tripped and untripped variations of the plot. The point where the trend ends could be approximated as the separation point. For the untripped polar plot, the trend of a consistent coefficient of pressure magnitude value ends slightly past the 90 and 270 degree point, which is basically the top and bottom of the cylinder. This is where we expect the separation to occur. The values past the separation point will vary greatly since the flow experienced by the surface of the cylinder goes from consistent to turbulent and erratic with vortices and all sorts of weird stuff happening. For the tripped variation of the polar plot, the trend of a consistent coefficient of pressure magnitude value ends much sooner than its untripped counterpart. This makes sense since the trip strip is tripping the flow to turbulent, inducing a separation point to occur much earlier. Overall, the value of this plot is great as we can identify the separation point of a body through a fluid, which is one of the defining aerodynamic factors for describing the flow around an object.
Next, we simulated the plots over time to get an idea of the coefficient of pressure variation with the actual test. For each RPM, the magnitude coefficient of pressure on the back of the cylinder seemed to remain relatively constant and not fluctuate like our group expected. This is most likely due to the vortex shedding happening a small distance behind the cylinder, so the true extent of the coefficient of pressure change was not measured. For the untripped data, the CP on the top and bottom of the cylinder was a lot higher than the CP on the trailing edge. This is due to the flow being in a state of semi-separation, as the flow is in the process of becoming separated from the top of the cylinder. For the trip data, the CP on the top and bottom of the cylinder was much higher than the CP in the untripped data. This is due to the trip strip making the flow completely separate before it reaches the trailing edge.
In order to calculate the pressure drag coefficient, we made the assumption that the ports on the back half of the cylinder would not contribute to the drag coefficient for the untripped tests. We believe that this assumption was acceptable because the coefficient of pressure did not change for the pressure ports on the back half of the cylinder. For our 500 RPM test, this assumption provided a coefficient of drag of 0.5987, which makes sense because this falls at a transitional point in the Reynolds number. For 600, we see a drag coefficient of 0.5437, and for 200, we see a coefficient of drag of 1.33, which is close to the tabulated value for laminar Reynolds number.
An untripped cylinder produces overall smaller CP on the leading edge as the flow is not fully separated as it passes over this point. A tripped cylinder produces a large CP on the leading edge as the flow has been fully separated from the cylinder. Different Reynolds numbers can cause different flow conditions around a cylinder. Our group concluded small Reynolds numbers can only be found in dense fluid flows, such as in water or oil, as even at 200 RPM, the Reynolds number is still very high. From the polar plots, you can see where the flow becomes separated. Some data may be inaccurate due to the trip strip being inconsistent over the entire length of the cylinder.